In this video, we're going to be discussing how we can easily calculate the total number of possible outcomes there exist for given situations. And so, in order to kind of lead into what we call the fundamental counting principle, let's consider the following situation. And here I have, it says, Mr. A attends a conference that's providing lunch. It says upon arrival, they ask him to make a sandwich selection for lunch, and I get to choose from these following options in these columns. So it looks like we have a bread option here. I either get to choose white or wheat, as well as what kind of meat that I would like on the inside, turkey, ham, or roast beef. So instantly what this says here is that I try to calculate how many different possible outcomes or combinations exist. And the question really is this: how many different sandwiches could we make? And I want to know why we get the response we do. So I think that we could start with this. In terms of what I could make here, I suppose that my initial decision is going to lie in the fact that I'm either going to choose white or I'm going to choose wheat. Okay, and I'm going to actually write these right here. We say white, or I could choose wheat. There are two possible outcomes there. Once I get to this juncture, though, I'm saying that it could either be white with turkey on the inside, white with roast beef on the inside, or ham on the inside, we say ham, or white with roast beef on the inside. And one could necessarily see here also that I have the same set of choices once I've reached maybe a wheat conclusion, but I could also do turkey here, I could do ham here, or I could select roast beef as well. So in terms of the total number of possible outcomes, what we're going to say is graphically what I've written right here, this diagram, this tree diagram, would show us that we have 6 possible outcomes. And these 6 possible outcomes would be white turkey, white ham, white roast beef, or wheat turkey, wheat ham, or wheat roast beef. Okay, so we say 6 outcomes. Okay, what I want to consider now, though, is this. We say if we alter this situation a little bit, what if I were to include a cheese option? So that is, we still have 2 choices for bread here, 2 options. I have 3 choices for filling options, but then what I do is I add in this option here that either says cheddar or American. So I want us to understand that if I were to do this now, out of each one of these branches, I could say, well, it's white turkey cheddar or white turkey American, but what I'm going to do is I'm going to get 2 more branches that spout out of each of these, and since I already had 6 initial branches, how could I easily find how many outcomes would be then? What I could tell you is, this is just different in that I have now 2 ways to interpret all of my former results, and so we're going to have 12 total outcomes, or 12 different possible sandwich combinations here, whereas up here we say we had 6 outcomes that could be given. Okay, so in terms of how we could easily calculate these things, I said given a situation like the 2 above, is there a way that we could have easily found out how many combinations would exist in general? And actually there is. What we're going to do is we're going to say we'll take the number of possible ways that each individual event could happen, that is the event of choose a bread and the event of choose a filling, and we could say, well, how many ways could they happen individually? In the first instance I said there are 2 ways I could choose bread, 3 ways that I could choose a filling, and what we're going to do is we're just going to simply multiply these together to get the total number of outcomes. And likewise down here we could have said choose bread, choose filling, and choose cheese, and there are 2 ways that I could choose bread, 3 ways that I could choose a filling, but then we doubled the number of possible outcomes because I said, well, now there are 2 different types of cheese, and essentially we would get 12 total outcomes here. So this method of finding the total number of possible outcomes for a given situation that exists, we give it a name and we call it the fundamental counting principle, or you'll see it abbreviated sometimes in textbooks, FCP, the fundamental counting principle. But essentially, let's go ahead and try to generalize this here. This is a very specific case, but it says 2 events. If I have 2 things that I'm choosing here, say bread and filling, we say if one event can occur in m total ways, this is the number of ways that the first event can occur, and we say and another event can occur in n total ways, then what is the total number of ways that both events can occur? Well, it says the total number of ways is just m times n. And so I say that this principle can be extended to include 3 or more events. 3 or more events. If 3 events occur in m, n, and p ways respectively, then the number of ways that all 3 events can occur is m, n times p. So we say that in general, the fundamental counting principle essentially states that if you knew how many ways existed for each individual event to occur, then in a given situation where events are occurring in sequence, like we chose bread, filling, cheese last time, we can just take the number of individual ways each thing happens and multiply them together. So in terms of what this is called, the fundamental counting principle is what we refer to it as, but we also call this the multiplication rule. Okay, and the multiplication rule essentially says exactly what we've outlined previously. So I want to use this multiplication rule, or the fundamental counting principle, to essentially determine the number of possible ways or outcomes that exist for these given situations. Starting with this one right here, we say a Nebraska license plate consists of 3 letters followed by 3 digits from 0 to 9. we want to know then how many different license plates could we formulate here? Well, the idea here is this. And I hope you see this here. When you determine the number of ways that something can happen, you'll notice that, at least in that last example where I had bread, I put an underline to represent each possible thing that could happen, or every individual event in this entire sequence of events. So this would be choose a letter, letter, and a letter. So these would be our letters here, letters. And these are going to be our digits. Notice I say not numbers, but digits here. And we say digits 0 through 9. So what we're going to do is we're just going to go through and list these. We say, well, how many letters could we possibly put in this first spot? And since we have free choice on any of the letters in the alphabet, we say in our Roman alphabet then, we have 26 letters, okay? Or English alphabet, let's put it that way. So we say 26 letters could be here. The question now becomes this: how many letters could we choose from to put in this second spot? Well, if I'm allowed to repeat letters, then I still have 26 letters that I could put here, and then I have 26 letters that I could put here. Now, looking at the digits 0 through 9, this is very important. Usually I get people say, well, there are 9 digits, 0 through 9. Technically, if you're counting the 0, 1 through 9 is 9 digits, but 0 also counts as a digit. So there are 10 different digits that we could choose from to put in this spot. 10 to put in this spot and 10 to put in this spot. So simplistically, we could just say that the total number of possible combinations, which is very many in this instance, is actually equal to 26 times itself 3 times and 10 times itself 3 times. As a matter of fact, we could write this in shorthand notation as 26 cubed times 10 cubed, or in other words, if we were to put this into a calculator, we would say 26 to the power of 3. And I could say times, in parentheses, 10 to the power of 3, in parentheses. So there's 1,000. We were taking that times 1,000. 17576. So 17576 with 3 zeros after it. So this is how many different, and I'm going to write it thusly, we say outcomes exist for this license plate experiment. So now I want to change the situation a little bit here, but it says how many license plates can be made if digits and letters are not allowed to repeat, okay? A little bit different in this situation. We say it's different from the first situation in that we can still choose from 26 letters to put in this first spot, but the moment we choose, let's say I choose the letter A. Once I've chosen A, if I'm not allowed to repeat letters, then I have one less letter to choose from my next spot. So this actually becomes 25, and the next one would naturally become 24. So this situation is different in that every time we choose a letter, if I can't repeat it, I lose an option for each instance here, okay? And the same thing goes for digits. I still have 10 digits to choose from to put in this first spot, 10 ways we could choose a digit. But once I choose one of those digits, I'm not allowed to repeat that digit. So, as a matter of fact, you know what? Let me take that back. I'm reading this again. It says how many license plates can be made if digits and letters are not allowed to repeat. I guess we can't repeat digits. I thought, for instance, there that we were not just repeating letters, but we can't repeat digits, I guess. So this will be a 9 and this will be an 8. So the total number of ways this can happen, and we'll just get our calculator out here. We know that obviously we can do less combinations because I can't repeat letters, but we say 26 times 25 times 24, and we take that times 10 times 9 times 8. The total number of possible ways we could do this is 1, 1, 2, 3, 2 with 3 zeros after it. So we get 1, 1, 2, 3, 2 with 3 zeros after it. And we're going to label this here. We say outcomes or possible license plates. Okay, and you can see that there are significantly less in this instance when we're not allowed to repeat. Okay, so let's try this again, our fundamental counting principle. Without me putting in the blanks for us here, let's go ahead and read through these. We say, justifying our responses, we're buying a sandwich. We have a choice of 5 meats, 4 cheeses, 3 dressings, and 8 other toppings. We say how many different sandwiches with 1 meat, 1 cheese, 1 dressing, and 1 topping can we choose? So the first thing I'm going to encourage us to do is this. Let's put a blank for each individual event that exists. And I don't typically write this, but underneath this we could write, this is our meat, this is going to be our cheese, this is going to be our dressing, and then this last spot right here is going to be a alternate topping. All right, but given these events that occur in sequence, how many ways could these events, how many total outcomes exist altogether? We could just say multiply the number of ways each thing can happen together. So we say 5 ways this can happen times 4 ways we could choose a cheese, 3 ways we could choose a dressing, and 8 ways we could choose that final amount right there. So we say, in terms of how many ways this exists, we say 5 times 4 times 3 times 2. We would get 120 different possible outcomes exist for making a sandwich here. Okay. Likewise, if we look at letter B here, it says how many different 7-digit phone numbers can be made if the first digit cannot be a 1 or a 0. So again, let's go ahead and write out the places for our digits here. We say our prefix code here. maybe not a prefix code, but the first three numbers, and we say 1, 2, 3, 4, these numbers here. We say how many ways could this happen? Okay, recall that there are 10 digits from 0 to 9. So if I say that the first digit cannot be a 0 and it can't be a 1, we're excluding 2 of the possible 10 digits. So we end up with 8 ways that this can happen. Now, as far as the rest of these digits are concerned, we have 10 possible ways that all of these could happen. So we say times 10, times 10, times 10, times 10. In other words, we would get 8 with 1, 2, 3, 4, 5, 6 zeros after it, since this is 8 times 10 to the 6, or 8, 1, 2, 3, 4, 5, 6. So there are 8 million different possible outcomes or different possible phone numbers given these parameters. Okay. So now, letter C, let's consider this. We have a multiple choice test, and this test has 10 questions on it, and each question has 4 choices to choose from. Maybe it's multiple choice. So we say, in how many different ways could we complete this test? The fact is, we need to write out our blanks that represent our 10 questions. And just to emphasize this here, I'll put 5 and 5, 4, 5. Kind of try to separate those a little bit. But since there are 4 ways to kind of choose an answer for this first question here, we say 4. There'd be 4 ways to choose on the next one. And you could see how this is just going to repeat here for each of these spots. We say 4s all the way across the board. So the shorthand notation is that there are 4 to the 10th ways, or 4 to the 10th outcomes for us to choose, or submit a test, I guess, randomly choosing things. And we say, what would this be as a figure here, a value? We say 104. So let's see here. We get 1,048,576 different outcomes for finishing this test. Okay, and then last but not least, we say on letter D here, if dressings were not a choice in example A, how many different sandwiches could be made? You could see how, if we were to go back up here and consider the situation that we had, if we cut out the dressing, then really all we're doing is we're saying then we have meat, cheese, and topping. And of course, there are 5 ways to choose a meat, 4 ways to choose a cheese, and then we have 8 ways to choose a topping. This would be the same thing as 20 times 8. So there are 160 different sandwiches we can make in this case. So the fundamental counting principle is a pretty easy thing to use. We use it quite a bit of the time when we're talking about counting situations. Cheers.